Hello and welcome to an FPGA vision video. In this video we have a look at clock domain crossing, and I will tell you what the problem, what the challenge in clock domain crossing can be. I will introduce you to an experiment to visualize this problem, and we will perform the experiment on an FPGA. So what is clock domain crossing? In a digital system, you often have several clocks. As an example, we take a CPU system for a computer with video output, like maybe Raspberry Pi. And then you have a certain clock for the CPU. This is typically in the 1 gigahertz area and depends on overclocking. Maybe if you have high temperature, you want to reduce the clock, but it's in that area. And you have a second clock for the video output. And this video output is lower frequency, typically in the range of 50 to 100 megahertz. I often use 720p format, which is 74.25 megahertz. And you might have more clocks on a system, for example, for interfaces, for the memory. But let's have a look at these two clocks. This is sufficient to illustrate the problem. And then you have data going from one clock domain, a CPU clock maybe, to a second clock domain, the video clock. And I will show you on the following slides what can go wrong. As a design function, we want to perform edge detection. So we have a signal A that comes from a different clock. And with this clock, we want to identify a change of A and give the value 1 as a pulse on the output Q. So our circuit stores the value A in B and then performs an XOR function to have a pulse here before the flip-flop, check this with the flip-flop, and then give the output Q. Here's the intended behavior. Signal A changes. With the next clock cycle, with the next rising clock, it's stored in B. Then we perform XOR of A and B. And here we have A is 1, the new value. The old value is 0, so A XOR B gives 1. We store that at the output Q, and we have a pulse for one clock cycle. Okay, so far so good. However, we have a potential problem. And this potential problem can occur if the value A changes just before the rising edge of the clock. So the value A comes from a different clock. It might change at any time regarding the position of the rising edge. And here it changes just before the rising edge. And now what happens is the following thing. This is early enough to be detected by the flip-flop of B. So it is stored in the flip-flop for B. However, the delay of the XOR prevents it from being stored in the flip-flop for the output Q, for the pulse. Okay, you might say, then it will be regarded in the next clock cycle. No, it is not, because it's already stored in B. So for the next clock cycle, A and B is identical again, so no edge, no pulse. The design really misses this edge. There's no pulse detected here. And this happens because you have the edge of the input signal just before the edge of the rising clock, which you cannot control. So how can we prevent such an error? The problem is that the signal A has several points for crossing the clock domain. So A goes into this flip-flop with a new clock, and by passing the XOR gate, goes also in that flip-flop with the new clock cycle. And this has to be avoided. So a signal must have only one point for crossing a clock domain, which means that a safe circuit would first take the signal A, perform the clock crossing to the new clock domain. So we have the signal A new, Then we have the flip-flop to store the previous, the old value of A, have the XOR, and then have the storage of the pulse. And all these flip-flops operate with a new clock. And here you see how such a VHDL design could be written. We have a process which runs in a new clock domain. The new value, the incoming value, is stored as the new value. The previous version of the new value is stored as the old value. We have an if statement comparing the old and the new value for A, and if they are differ, if they are not equal, Q is 1, otherwise Q is 0. And this VHDL gives a safe design. Let's do an experiment for clock domain crossing. And for that we use the design of a video generator that I have introduced in several other lectures. The code for the video generator and the code for this experiment is available on GitHub. Here you see the VHDL code for the experiment. It is based on videogenerator.vhd, and for more background on this design you can have a look at the other videos in the lecture. The design uses a clock, which is the video clock of 74.25 MHz for 720p video. And we have an input signal for controlling the video generation. And this is this enable in. And it comes from the CPU. It's with a CPU clock. So exactly the setup that I illustrated earlier. Then we have here the problem where the enable signal, enable in, should be stored in the clock domain of the video signal, but we omitted that. So this is the problem here, that we don't perform this storage. And then we have here, starting at this position, our video generation. What you see here is that we generate a red rectangle which serves as a reference. And then we generate a second rectangle which changes the size and changes the color. So it's green and blue. It starts as a small green rectangle. And if we change something in the enable signal, the color signal is inverted and the end position is increased by 100. So if we press a button, if we change an input, the size changes from 500 to 600 and changes to blue color. Then it changes to 700, changes the color. It goes larger, and so on, and so on. And when the position reaches 1000, it starts again at 500. And the generation of these rectangles is controlled here. So you have starting position and end position. And here you see the color. So if rec color is 0, you generate a green signal. If rec color is 1, you generate a blue signal. With this code, we now do simulation. The test bench is also available on GitHub. And we will see that everything is working fine in the simulation. So the basic idea apparently seems to be correct. But it's not, as we'll see later. Here's the test bench. It gives input signals to the design and stores the output as an image file. And in this area, you see handling of the input signals. In the simulation, we monitor the input signals and the video output. After some seconds, the simulation is completed and we can zoom out so that we see the complete simulation run. We see that the input signals change 6 times. And if we zoom in, we see here detail. And this is now the output of the test bench. So we don't get 6 separate images to save some simulation time. We have all 6 cases in one image, and with every switch of the input signal, the rectangle changes position and changes color, and after 6 switches, it goes back to the start position. Now we go from simulation to a real circuit. And for that, we use the FPGA remote lab of Hochschule Bonn-Rhein-Sieg. It's available as a free resource, so you can also perform the experiment and check the result that I show you now in my demonstration. We perform synthesis of the FPGA. Don't forget to import the pin assignments. And then, after a few seconds, the design is completed. We generated the design for the Cyclone 4. This is the control panel of the remote lab. In the center, you see the FPGA board, and on the right, you will see the output of the FPGA. The FPGA also can process an input image, but we're not using this for this experiment, so you can disregard the input image on the left side. For our experiment, we now upload the binary of the FPGA design. It's loading and we see the generated video. Now we switch the different inputs and you see that with every switch of the input, the next position of the rectangle is displayed. And now it has the maximum size. It's equal to the red rectangle. And here it misses now the switch. So we switched the SIG input and it did not change the position. And now you see another error. So the size changes, but the color did not change. So it stayed blue. You see that the design has problems in detecting the input signals just as we expected it to do. Now we repeat the experiment to see that this was not a very seldom event. I can assure you I did the experiment several times and nearly every time there was an error. And this is a very interesting error here that you see in this video. At the end of the cycle, when the rectangles should switch to the starting position, it misses this statement. And the rectangle goes larger and larger and larger. So this is a very interesting error to see. It's an unsafe design and should not be released. So you can try out the behavior, maybe using different FPGAs and doing little statistics. We have a Cyclone 4, 2 Cyclone 5, and a Cyclone 10 at the moment. However, the main exercise is correcting the problem. And this means using an input flip-flop. So you define the enable signal, and then you store the input signal into an internal flip-flop. This is the input flip-flop. And then you use the signal that comes from the flip-flop that has crossed the clock domain for the edge detection. So here you use enable, and here again you use enable. Also, you saw that the box extended beyond the range of 1000. This is caused by this being a check for equal 1000. This could be corrected to larger or equal 1000, but that's not really a problem. The problem was caused by the clock domain crossing. So I hope you learned something about clock domain crossing. Finally, a personal note. I'm currently on leave from Hochschule Bonn-Rhein-Sieg and now working as manager and scientific director of the Bavarian Institute for Innovative Teaching. I'm still working in education, and as you can see, I'm still interested in online learning. Thanks for watching.